Hello, hello. The class will start shortly. Hello everyone. So today's lecture, or the next chapter in our story, it has to do with interpolation, all right? And like I always start with things, I'd like to start with a practical example. All right, so what you're seeing here is a set of temperatures versus hours of day recorded at my house in Sandy, Utah. And 0 means midnight, 1 o'clock is 1 a.m., 2 is 2 a.m., and so on, all the way to 6 a.m. So on the x-axis, I'm putting the hour, time of day, or hour of day, starting the count from midnight. And on y-axis, I'm putting the temperature, right? So midnight was about 75. This was, I think, sometime mid-August. We do get some really nice canyon winds in the evening, so the temperatures drop really nicely in the evening and the wee hours of the day. And so 75 then goes down, 74, 73, and so on, all the way to 69 at 6 in the morning. Right? So my question to you now is, what is the temperature at 5:30 a.m.? Okay. Now we're going to switch to Zoom and do this discussion over Zoom. How did that go? All right. So now we're back on Zoom to do the class activity. I hope once you're done, I'd like you to please mute your YouTube. Please mute your YouTube. Okay. So now we switch the discussion to Zoom. Mute your YouTube, but it will be recorded. When you come back to it, my audio is going to be recorded. Okay, so we got 30 seconds over here. What is the temperature at 5:30 a.m.? 5 and 6. So, okay. Okay. Before we get there, just like you said, what is the temperature at 5:30? So Soviet was saying it's probably the average between the two temperatures, the one at 5 o'clock and the one at 6 o'clock. Agreed? That makes sense, right? 5:30 splits the interval between 5 and 6 right in the middle. So it would make sense that the temperature between 5 and 6 a.m. is probably 70 plus 69 over 2. So that's like 69 and a half. Okay? All right, so now we're going to switch back to the slides. I know this is going to be annoying with the class activities, but once I get a stretch of lecture without activity, it will be better. All right, so I'm going to switch back to the YouTube now. You can unmute yourself on YouTube, unmute me on YouTube. Okay, so like we discussed just now, the temperature at 5:30 a.m. is likely to be the average between 70 and 69, right? Because 5:30 just kind of cuts the interval 5 and 6 right in half, and the temperature is going to be right in the middle. That's 69.5 Fahrenheit. That's acceptable, okay? All right. So now I'm going to ask you, what is the temperature at 5:17 a.m.? So 517 doesn't cut 5 and 6 in the middle, right? So it's closer, going to be closer to 70. So what would you do? Describe to me the approach that you would take to find the temperature at 5:17 a.m. Now, in terms of hours of day, 5:17 a.m. in terms of the counter from 0 to 24, that's 5.28 hours. Okay, so 5.28 hours have passed from midnight until 5:17 a.m. So I want you to take a minute to now describe what would you do to calculate the temperature at 5:17 a.m. I'm going to switch to Zoom now, and I'd like you then to mute your YouTube live stream. Are we all on Zoom now? Okay. I have about 30 seconds left. I just want you to describe what you would do, to calculate the temperature. Okay. So as a reminder, this is the slide. All right, do I have any takers? Go ahead. Okay. 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 So what Carl has described is the answer that I'm looking for, just phrased differently. And I see in the chat, Emily has put in a formula, but I don't know what y2, y1, x2, and x1, and y3, y1, etc. You're probably doing the ratios of the triangles, which is correct. But what we want to do here is try to fit a line. That's the easiest, given those two data points, we have no other data. The simplest thing you could do is fit a line between those two data points, correct? And then find where that line intersects the 5.28, the 5.28 point, okay? So I'm gonna switch back to the slides and then assign you one other activity, okay? Okay, now we're back on this live stream. Like we discussed in class, what we want to do here is draw a straight line. I'm kind of behind the slides over here, but you see a straight line drawn between 70 and 69, all right? And that is intersected at that blue triangle over there along the 5.28 hour vertical line, okay? So now we have a rational way of finding any temperature at any hour in between 5 and 6, okay? So I want you to go ahead and try to give me the equation for that straight line. And that straight line is going to be an equation expressing the temperature versus the hour of day. So if you think of the straight line as y equal ax plus b, x is going to be the hour of day, y is going to be the temperature at that hour of the day. So I'd like you to find that equation for the line so that we can just simply then apply it to whichever point we are interested in. Okay? So now I'm going to switch back to Zoom. Please mute your YouTube. Okay, I'm back on Zoom now. Many of you already have the answer. Looks like you are far ahead from what I expected, which is great. But I'd like to give your colleagues a chance to try to work this out. So to help you a little bit for those who are trying to figure out what they need to do, you just need to find the equation for the straight line. And the equation for the straight line requires two quantities, the slope and the intercept. So ax plus b, a is the slope and b is the intercept. Okay, so you got to find those two quantities. You know how to do this, right? Um, uh, I'm trying to figure out how I can record the discussion through the YouTube stream. I couldn't figure it out today because I have to install some additional software and drivers. So what I will do, probably you're not going to be heard through the YouTube live stream. So I cannot record both the Zoom discussion and the YouTube live stream because the Zoom discussion is just going to be a discussion. There's not going to be slides. So ideally, I want to pass that Zoom discussion through the YouTube stream. But for now, that's not going to be recorded. Okay. All right. Okay, so time is up. Let's see. Do we have any takers? Do we have any takers? Hey, Adriana, do you want to try? I saw you working really hard. Do you want to give this a shot? At least describe what you tried to do. Go ahead. Mm-hmm. Uh-huh. Yeah, correct. Yes. Excellent. That's really good. Okay, so I'm going to switch now to YouTube to explain what Adriana did. Okay, so this problem boils down to simply finding the equation for the straight line between the point 570 and 669. So 669 and then 570. And we just need the equation for the straight line that passes through these 2 points. It's very easy to do. You first write down the equation for the straight line. You're accustomed to doing y equal ax plus b. I want to put it here, t equal mx plus b. M for the slope, t designates the temperature, and x specifically signifies the time of day. So time of day in hours, because our counter starts from 0 to 24, not 5:30 a.m. You need to translate that into a fractional number. So the slope, just simply like Adriana said, it's rise over run. So that's 69 minus 70 over 6 minus 5. You can do it that way, or flip it the other way around. You could do 70 minus 69 over 5 minus 6, as long as the pairs are consistent with each other. And you get a slope of -1. Critical thinking over here, you say, should the slope be negative? Yes, absolutely, because it's a downward going line. So that's good. At least we know our result is consistent with our understanding of how slopes behave. Next is you want to find the intercept. That's the value, this constant b. And you can do this any one of two ways. You either evaluate the equation of the line at the point 570, at the pair 570, or at the pair 669. Is going to give you the exact same answer. So I chose to put it at the pair 570. So t at 5 hours is equal to 70, but that's also equal to 5 times the slope plus b. So that's minus 5 plus b. That gives you b equals 75. And then finally, you get the equation for the straight line between these 2 points. That's minus x plus 75. And you simply apply that to any point in that interval between 5 and 6, right? So in this case, t at 5.28, you just plug in the number and you get 69.72 Fahrenheit. Critical thinking, yeah, that makes sense. It's going to be value of the temperature based on this is going to be closer to 70 over here than it is to 69. Hence the 69.72. It's closer to 70 exactly as we expect, all right? And what you just did is linear interpolation. And I'm sure some of you have done this before in some of your other classes, and that's great. But for those of you who haven't seen it, you just did linear interpolation. So now I'd like you to help me generalize this. And here's your next assignment, is that we're going to take this example that we did, hour of day temperature, hour of day temperature. We had these 2 points, our temperature, hour 1, temperature 1, hour 2, temperature 2. We had these 2 pairs. We're going to call them x and y, x for independent variable, y for dependent variable. We're going to take 2 arbitrary pairs, x1, y1, x2, y2. And I want you to find the equation for the straight line between these 2 arbitrary points, okay? Those could be hour of day temperature, pressure, viscosity, whatever, okay? So go ahead and take 3 minutes to do this. And I'm gonna switch to Zoom. Back on Zoom. You can still see the slide with the activity on your YouTube stream, but please mute the YouTube stream. We have about 20 seconds. Let's see. Porter, would you be ready to explain to us how we would go about and do this? Go ahead. Mm-hmm. Okay. Mm-hmm. We're not trying to find Y2. We're trying to find, sorry, did I misinterpret what you said? Sydney, did you have something to say? That's right, to find. Mm-hmm. Yeah, so this is just a simple exercise in finding the equation of a straight line, giving two pairs of numbers or independent dependent variable. Our goal is not to find y2 or y1 or x2, those are given to you, right? They're given to you, just like the hour of day and temperature example that we just did. Our goal is to find values in between x1 and x2 and y1 and y2. So if I were to tell you find the y value at some point between x1 and x2, that would be the question for this linear interpolation. Okay, so I'm going to switch back now to the live stream, and I can explain to you what Porter and Sydney were telling us. All right, so you got it right on the Zoom meeting. So what we want to do is simply find the equation y equal mx plus b over here. And we have 2 points, y1 equal mx1 plus b and y2 equal mx2 plus b. So you could, for example, just do what Porter was saying, is just find the slope m and then find the intercept, or you can define a linear system of equations. Now that you learned how to do systems of equations, you can simply say, well, these are two equations with two unknowns, right? You know y1, x1, y2, x2, and all you need to do is you want to identify, let me see, m and b. Those are the unknowns. You agree that this is a system of linear equations, right? And then you can translate that into matrix vector form, okay? And then solve the system of equations for m and b, and then you plug them back in and you get this convenient formula. Many of you might have a different form of this formula. You can rearrange it so that it's clean this way. I like this way, it's clean. Now, I want to stress the importance of the linear system of equations. Although you could do the slope intuitively like you did by hand and then find the intercept, that only works for linear interpolation. Once we go into higher order interpolation, you are going to be bound to do linear systems of equations this way. So that's why I wanted to illustrate to you this, the importance of trying to describe this as a linear system of equations. So you might think that you haven't learned much today, right? But trust me, there's going to be a lot to learn now as we expand this. The advantages of linear interpolation is that it's really easy to use. You could do it while flying to a conference or to visit family, and somehow, like, this happens to me all the time. I'm in the airplane and my mind starts thinking and drifting. I'm like, I end up wanting to calculate things like, the first thing I like to do is calculate the Mach number at which we are flying. And then, but obviously, clearly, you want to know the speed of sound at the altitude. And, I start running some calculations on a paper just for the fun of it. And then I share with the, person sitting next to me, and they're like, just shut up, leave me alone. Don't explain to me the physics of flying. And especially it gets interesting when I tell them about the structural integrity of airplanes and how safe they are and what could break, etc. So anyway, you don't want to be sitting next to me on an airplane. But linear interpolation is something you could do by hand, back of the envelope calculation, okay? And it's my first go-to method to find and interpolate data. The disadvantage is that it is not very accurate for nonlinear functions. Okay, so or nonlinear or data that is distributed in a nonlinear fashion. All right, so let's expand now the scope of what we were thinking about. I just gave you 2 points. Now we're going to look at entire data sets. Okay. So what I'm showing here is a table that I took from a book on heat and mass transfer that you will study in probably, I'm not sure if we changed the textbook, but this is by one of the most famous people in heat and mass transfer in Cropera. And it's a table giving us the properties of air at atmospheric pressure. And those properties are described here on the first row, on the first column, sorry, you get temperature, and then you have density, coefficient, heat transfer coefficient, and viscosity. Okay, so these are just properties. Why do you need those properties? You're going to learn that we need them in practice when we're calculating heat transfer, when we're calculating properties of reactors and processes, even biological systems, etc. We're going to need these properties. Okay, but oftentimes data is described this way. Okay, so we only have discrete data. We do not have continuous representation of data or like a nice function that you can plug numbers into. So for example, given this data, you might think, okay, what is the density of air for at 132 K, right? So you need to do some form of interpolation between the data. And the idea of interpolation, the general idea, we just did linear interpolation, but the general idea is to fit a polynomial function into the data, essentially just connecting all the dots. So if you were to plot y values versus x values, or dependent variable versus independent variable, and you were to connect the dots, that is fitting a polynomial in those data. Now, you could connect them via straight lines, that's linear interpolation, or you could connect them with squiggly lines or curved lines. That's general polynomial interpolation. Polynomials are interesting because any point in the real plane, in the xy plane, you can find a polynomial. You can define an arbitrary polynomial that passes through that point. That's why polynomials are powerful and very useful. Now, a straight line or linear interpolation is simply a polynomial of degree 1, right, of order 1. Okay, because there's a x plus b, the power of x is 1. That's the simplest, the simplest polynomial you could get. Well, the simplest one is of order 0, x to the power 0, right? But you know, the first order polynomial with the function of x is just a straight line. Okay, so the idea would be to choose the polynomial function. You can define the order of that polynomial. We'll see what that means in a few slides. Then solve for the coefficients of the polynomial, just like we did with the straight line. We were looking for the slope and the intercept. When you go to quadratic and cubic polynomials, you have more coefficients. Those are the A0, A1, etc., that you need to solve for. And then once you have those coefficients, you have a formula, okay, that you can apply at any point in those data, in the data that you are given. Okay. So going back to this table, which we're going to work with a little bit when we do our coding activity as well, the first thing that I like to do is be familiar with the data, flirt with the data, understand the data. Okay, and the best thing you could do is to visualize it. And this is what I've done here when I'm looking at the temperature or density versus temperature. So I chose my independent variable to be the temperature, and I'm plotting the density versus temperature. And then you see a trend. You see this nice kind of quadratic profile going down like this for the data, density versus temperature, okay? And once you are familiar with this data, you can start probing it. Now, we just talked about linear interpolation. Linear interpolation works only between 2 points. Why? Because you have 2 unknowns in the straight line equation. Those are the slope and the intercept. So you need 2 equations. In other words, you need these 2 known points. And then you could imagine that if you could fit a straight line between each pair of 2 points, then, you can find an interpolation for the entire data set. And this is what you would get. So if you were to zoom in to any region of the plot, you would be getting straight lines between each and every 2 points. Fair enough and simple. Now, clearly, when you are given very large data sets, this is manageable right now. You got 15 points, and still it's annoying sometimes to type or to look through tables, right? But if you're given thousands of data points and you want to do linear interpolation, it doesn't make sense for you to go and find these 2 points. So we need a mechanism through Python or through a programming code that will allow us to do all of this. And this is exactly what we're going to do next, is we're going to learn how to do linear interpolation in Python. Now, you know how to do it theoretically. You have the formula by hand. You can do the slope, etc. But when you have very large data sets, data that is not necessarily just showing one trend is going up and down, etc., you don't want to worry about finding where the 2 points are and interpolating them. You just want Python to go ahead and find the spot for you and do the interpolation automatically. And thankfully, Python provides that through the function called Interp, provided by the NumPy library, the equivalent of which in MATLAB is Interp1D. I think many of you are familiar with that. Now, when you look at the interp function, and my hand cannot go behind this, so I'm gonna try to put my hand above this, okay? So you have the, I'm defining the numpy.interp as ye, and I'll explain my nomenclature in a second, is numpy.interp. It takes 3 arguments, xe, xi, and yi. I use the I as input, okay? So automatically xi and yi designate the independent input variable and the the dependent input variable. So in our examples we just did, if we were to look at temperature at a given time of day, temperature versus hour of day, our input independent variable is hour of day, and our input dependent variable is temperature as a function of hour of day. For the example of density versus temperature, our x input, the independent input variable, is the temperature, right? And the dependent input variable is the density. Keep that in mind because that's going to be critical when you are playing around with data. Always don't think of it as xi, yi. Think of it as independent and dependent variable, okay? Because ultimately, you are calculating the value of the dependent variable at a different independent variable point, okay? So that's what xi and yi are. Those are generally vectors of data. So you just give the function the entire data set that you have. Clearly, they both have to be the same size because for every x point, for every independent variable point, you need to have a dependent variable point, okay? Now, the other argument, the first argument, xe, is where you want to interpolate the data to, okay? So, and that is a independent variable, okay? So in other words, for the examples we did, that's the 5:17 a.m. or the 5:30 a.m. or the density at 132 degrees, the 132 degrees, that's the xe. And finally, your result is going to be the ye, that's the value at the interpolated point, okay? So now we're going to switch gears and do a coding activity together. We're going to do it on Zoom. Okay, I'm going to try to record it on the live stream. We'll see how that works out. Okay, but we're going to now switch back to Zoom and do the coding activity together. I'd like you to download the notebook called Interp Activity One.ipynb. I have a typo over here, from the interpolation module on Canvas. Go ahead and download that, put it in your Jupyter Hub, whatever that is, and open it, and we can work on this on linear interpolation together. Now I'd like you to mute your YouTube stream, okay, as I figure this out. And this will be recorded on the live stream. Okay, but I want you to see it also on Zoom. So give me a second while I navigate. Okay, anyone having similar issues? Same thing happens to you? Still not working? It downloaded fine, Interp Activity One.ipynb. So try to go to the files if you want. So when you click on it, on interpolation, and the interpolation module should take files directory. Anyone successfully downloaded this notebook? Okay, so it looks like there are some of you are having problems. I don't know what's going on your end, but try to figure it out. Maybe refreshing like 1,000 times possibly. Okay, so I'm gonna here right now try to figure out how to share both on Zoom and on the YouTube. Okay, interpolation. So for those of you who have downloaded this, just go ahead and start playing around with it, please. Okay. Okay. Now, since we're on Zoom, I'm gonna share the screen with you. Okay, so I'm sharing on Zoom. Can you see my window? Can you see the coding activity? Yeah, on Zoom. Okay, great. All right, so this is called Interpolation Activity One. And what I've done here is I imported a few things. And as you've noticed, every time we do some coding, I'm gonna introduce something new that will probably be very useful for you. So, but by default here, I'm always importing NumPy. It's one of my favorite libraries, but I also imported Interp from NumPy so that I don't have to do np.interp every time. Now I added this script called this line called Matplotlib Inline that forces all plots to show up automatically. And then after that, importing Matplotlib. But you notice here I added this magic line. It does something in the background, but what the goal of this line is to produce vector type graphics inside your notebooks. So for those of you who are not familiar with vector graphics, they're like the highest quality. They're like fonts, you know, like a text file or a Word document. You zoom in infinitely many times and you can still see perfect structures of the letters, etc. This is what SVG does. It stands for Scalable Vector Graphics. What this does is it forces the notebook and Matplotlib to produce the vector quality graphics. Okay, So now consider the temperature and density data for air at atmospheric pressures. These are given in the notes in class and provided here for your convenience. So what I did here, I input the array for the density, and I called it rho, or you can type in backslash rho and then press tab, or just call it rho, R-H-O, okay? And that's this array in kilograms per cubic meter. But for the temperature, I know that all my data was given to me in intervals, like fixed intervals of 50 degrees, so 100, 150, 200, et cetera. And so I created that via a linear space. In general, those data will be given to you either through text files or you have to input them manually. Okay, so just for this example, we were able to do a linear space for convenience. And if you go ahead and run this, it's going to throw an error because clearly you need to run the first window, the first cell. Okay, now this cell. Okay, so now you are getting the temperature here, 100, 150, 200, and so on, all the way to 1000. That's exactly what the data was telling us. Okay. Now, the first thing to do when presented with data is, like I said, get familiar with it. So I would like you to go ahead and plot the density versus the temperature of air. Okay. And some of you have filled this up. Do you want to tell me what I need to put in here? I have this. Got it. And then over here, rho, correct? Thanks, Mitchell. And then KO. So for those of you who are also new to MATLAB, what I'm doing here is I'm adding a symbol and a color for this plot. The symbol is O, K is black. Okay, now don't ask me how Python figures this out, but it does. Or you can put OK and it will figure it out. Okay, so if I press Shift Enter now, it should produce this nice looking plot for me. Now look at the SVG quality, right? In the past, it used to be all pixelated. And for those of you who are inclined to have an artistic vision, nothing irks me more in this day and age than a pixelated figure or plot. It's like something from the 50s. They even used to do better in the 50s. So anyway, SVG is going to give you high quality graphics. When you export your plots, export them as PDFs, because that is going to give you a scalable vector graphic as well. Okay, don't export it as PNG, or if you want to export as PNG, make sure the resolution is like 1200 DPIs. Okay, now I always, when I have scattered data like this, and this is advice to you, always plot it with a symbol and do not connect the symbol. Because when you connect the symbol, you might get misleading or you might misinterpret the data. So for example, I'm going to eliminate the O symbol over here. So what it will default to connecting the dots with a straight line. And this is what it does. So this gives you the illusion, that this is continuous data, for example. Whereas, no, I enforce the idea that this is scattered experimental data that was observed experimentally. Okay. Now, in other cases, when the data is completely oscillatory and more complex than this, connecting it with lines like that is a terrible idea. It will mislead you. So I always like to plot it with a symbol. Okay. So always plot a scatter. Yes. Sure. Of course. Braden is saying, let's put a grid. No, it's just extra code because when I put LaTeX over here, you see these dollar signs. If I don't put this guy, it's gonna print, well, okay, look at this. It's gonna print out this silly thing over here, tax 0, 0.5, etc. So I put a semicolon to prevent it from doing that, okay? But if you put something behind it, like grid after it, it doesn't matter, okay? All right, so always plot a scatter without connecting the dots. However, to show what linear interpolation for the entire data set might look like, just simply connect the dots with a straight line. And you can just do this by adding a hyphen next to the symbol. So go ahead and do that. We had plt.plot, t, density. Okay, so on the x-axis, we have the temperature. On the y-axis, we have the density. And over here, we have KO or OK hyphen. And now you get this straight line connection. So by default, all plotting software, at least that I know of in my lifetime, when you try to plot and connect the dots, you're just going to connect them with straight lines. So that's the equivalent of conducting linear interpolation on an entire data set, or how it looks like. You take each and every pair of points and connect them with a straight line. Okay? All right, so now we're going to start playing around with this data. Now I want you to use the interp function to find the density at T equal 132 Fahrenheit. Remember, the interp function, if you're in doubt, you open the parentheses and press Shift Tab. It gives you the signature, the function signature, X, XP, and FP. In my slides, I put XE, XI, and YI. Remember, these last 2 points, two data points over here are the input independent variable and the input dependent variable, okay? Those could be the entire data set or just 2 points, okay? And as is where you want to interpolate the data to, right? So let's see, what do we got here? What should I put here? Weston, 132, okay, who said that? Who said that? Braden, okay. Okay, why? Got it, you're right. Excellent. Okay, Braden, so let's do this in a, so what Braden said, he did some critical thinking on this. He said, okay, so I used the interp function. I took the entire data, T and row, the entire data set, okay? And I did linear interpolation to find the temperature at 132. Now, internally, what Python does, it looks through this data and finds the 2 points that are before 132 and after 132. Finds those 2 points and then does linear interpolation over there. So in other words, for 132, that's this point over here between the first point and the second point. So Python finds these 2 points and says, oh, 132 is somewhere here. So I'm going to go ahead and do the linear interpolation here and evaluate it at 132. Okay. Now, what Braden said is, let's do some critical thinking. We got a value of the density. So this 2.775 is the density at 132. Anyone disagree? Okay. So the value of the temperature at 132 is of the density at 132, 2.776. All right. Now Braden said, let's make sure this makes sense. Okay, so how do we do that? We just look at the data and see if this point falls between the data that is given to us. So 132 is somewhere over here, okay? And it should fall between 2.4, let's say, and 3.5. So 2.77 is somewhere over here, which is exactly what we expected, okay? A better way to do this, or another way to do this, is to actually plot this data point, okay, on the plot itself. So what I'm going to do, I'm going to create a new X and Y values, 2.775528, and I'm going to plot them on top of these original data, okay? Then plt dot plot, let me call it XEYE, okay? XEYE, and I'm going to do a red square. See? Isn't this cool? Critical thinking, and we better make sure that this square lies on that straight line between the 2 points, okay? And we can do a grid. Okay. So now we use the interp function. We took the entire data set, T and row, and we interpolated to 132. We could have taken just the 2 points at 100 and 150 and did the interpolation, but why worry about that? Just do the interpolation on the entire data set, okay? Now, I'm going to ask you to find the density at a few more points, 123, 251, 443, 599, etc., etc. Again, use the NumPy interp function to do this. So go ahead, help me, or take a moment. So here we, yes, who is speaking? Hey, Mitchell, yeah. So let me ask you this, does it matter? Why do you want to do a conversion? Why do you want to do a conversion? Oh, I see. I apologize. This is a mistake. Got it. You're right. It is in Kelvin. Okay. You are correct. I apologize. It was my fault. It was a typo. Okay. Yes. If it were given to you in Fahrenheit, and if I asked you to find it in Fahrenheit, but the data was given in Kelvin, you better convert to Kelvin and then do the interpolation. Good catch, Mitchell. Thank you. This is my mistake. Okay. So now we go back here, all right, since let's see. All right, who am I gonna pick for this? Let's see. Sophia, would you like to help us figure this out? Okay, go ahead. Okay, so or the let's use array because specifically there's not a matrix, right? So just call it array or the vector of points at which we want to find the density. So these are all the temperatures at which I want to find the density. So I want to find the density at 123, at 251, etc. And then do you have the next one? Okay. So what Sophia did here, she assumed that the interp function doesn't only interpolate to a single value, it also interpolates to an array of values, which is correct, okay, because I described that in the slides. And also in the function signature, it tells you over here that you can, instead of giving just one value to which you want to interpolate, you can give an array of values, and it's going to interpolate at each and every one of those points. So what do I expect my answer to be over here? What do I expect the answer to contain? Abby? Okay, what do the answers correspond to? Correct. So I print this, and what we got is 2.995. I claim that this is the density at 123 Kelvin. 1.39 9, that's the density at 251 Kelvin, and so on and so forth. Okay. Now, plot these points on top of the original data. If I pick your name, forgive me if I know some of you had opted out from being called upon. So I don't have that list in front of me right now, but forgive me if I pick your name and you had opted out. Just tell me that you had opted out, or don't answer. Let's see. So I see the same people in front of me over here. Let's see. Nathan Rami. Do you want to help us with this? Okay, looks like, all right. So let's see, David Zhu. Yeah. All right, so what we've done here, the same thing we did a moment ago when we plotted this red square. We took the interpolated data. Now this was given to us as an array for X values and independent variable values, and we got an array of dependent variable values, and I'm going to plot them as red squares on top of this, and look at that. Okay, that's great, right? Now, with this is very powerful if you don't see it, and this simple linear interpolation is so powerful because you are going to face this. You're going to have a lot of experimental data that looks very complicated, and you're going to want to find values in between. My go-to tool initially is to do linear interpolation until it fails me, okay? So now, before we finish off with linear interpolation, just like we did here, we created, we tried to find the temperature at 123, 251, et cetera. I want you to create a linear space for your own linear space that spans the entire data set from 100 to 1000 with 100 points. So I want the data given to us, we only had 19 temperature values, 100, 150, 200, all the way to 1000. Now I want you to create 100 values for the temperature, do the interpolation at those points, okay, and then plot that. So lin space, you want to start with a point and end with a point. This is here lin space, create a bunch of points for the temperature, 100 specifically. All right, let's see. Megan, you want to help us fill in the blanks? Why? Why not 100 to 2000? That's correct. Okay, so I'll make a comment on that in a little bit, and then you plot it, and this is what you get. You just get a finer representation of the data, but all the interpolated data is going to fall on those straight lines. Now, what I asked Megan is, why did you choose those bounds for the lin space? Why did you choose 100 and 1000? Why didn't you choose 0 to 2000? I mean, let's try that. Let's do 0 to 2000. Let's see what we get. Look at that. We got junk data outside our original data. Okay. Why? Megan answered specifically that the bounds of the data that we are given, we can only operate in those bounds when we are doing interpolation. It's called inter for a reason, because it's inter between the points that are given to us. What we just did here for the points from 0 to 100 and 1000 to 2000, we did what's called extrapolation, and a very bad extrapolation for that matter. Okay. I don't know. I don't want to try to do that, especially using linear interpolation. So don't do it. It's a bad idea. You don't have information about what's going on over there. You only have information about what's going on in between. The way linear interpolations are built is that you operate on the points that you have. Okay, you can extend one of the straight lines out and one of the other straight lines the outside, but that's still a risky business. What if some other physical mechanism takes place as temperatures drop, right? And then you reach some nonlinear behavior over there. Okay, that is not going to work. All right. Yes, Carson. We are going to look at regression after we finish with interpolation, but interpolation should strictly be used to interpolate between data. Do not go outside the bounds. You could, for example, say, I'm going to take the straight line between these 2 points and push it out, but you don't know if that's the behavior outside these points. So it's a very risky business. Regression, on the other hand, as we will learn later, regression looks at the general trend of the data, and then you might be able to extrapolate that way. Okay. But interpolation, notice with the interpolation, your interpolant should pass through each and every point of your data. Okay? All right. So I'm going to give you a couple of minutes break, and then we will switch back to the YouTube live stream. Okay? All right. Time, everyone. Okay, before I continue with interpolation, polynomial interpolation. Let's finish today's lecture with inverse interpolation. I felt you deserve a little break from all of this before we finish off this important topic. So now, so far, we have worked with looking at the temperature as the independent variable and the density as the dependent variable. So we thought of this as given a temperature, find a density, okay? Suppose now we want to invert that question and say, you know, I'm measuring a density of, let's say, 2.34 kilograms per cubic meter. At atmospheric pressure, what do you expect the temperature to be? Okay. Now, from the table, if you look at the data that I gave you, 2.3364 kilogram per cubic meter should correspond exactly to 150 Kelvin. Okay. So now I want you to use the interp function. Okay. Invert the dependent and independent variable and try to get me the density, the temperature at a density of 2.3364. Okay, so I'm right here. So now we inverted the meaning of xi and yi. Previously, we were interpolating for new values of the density at a given temperature. Now we're switching that. We're going to interpolate, find new values of temperature at a given density. So go ahead and try this out. Okay, I see some nods. I see some surprises. All right, do I have any takers? Go ahead, Sam. Correct. Mm-hmm. 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 Correct. That's correct. I agree with that. Now, what did it give you? 1,000. Okay, so now critical thinking. Let's look at our data just up here. We're saying that for a density of 2.3364, which is somewhere around here, okay, I expect a temperature of 150 exactly from the data because I have a data point here. Instead, the interp function gave me a temperature of 1,000. This doesn't make sense. Okay, does anyone disagree with this now? Try it on, put it in, and see for yourself that you're getting a wrong value for temperature. So clearly this doesn't make sense. Now there's a caveat for linear interpolation, and that caveat is that the X data, the independent variable data, should always be sorted in increasing order. Should always go from small value to large value. When we were first interpolating the density with the temperature being the independent variable, if you print T, notice T is going in increasing order, 100, 150, 200, etc., etc. And the corresponding values for the density were matching values. Now that we switched the order of dependent and independent, if you print rho, what is rho? Rho is in the reverse order. It starts from high value to small value. And the interp function, unfortunately, cannot figure this out. And sometimes you might not have a monotonically decreasing or increasing or decreasing function, you might have data all over the place. So what you need to do is sort the data in the correct order. There are a few sort functions that you can use, the most powerful and most useful of which is called Arcsort. And that what Arcsort means, it means give me the arguments that sort the array in increasing order, okay? Now remember, the caveat here is if you sort one of the arrays, you gotta adjust the other array, not sort it, you gotta adjust it by the correct order that you sorted the first array. So the best way to do this, and you'll learn this and forget about it, is use the function called arcsort. So what I'm gonna do here is first just use mp.arcsort row. What I claim this will return is gonna return an array of indices that will sort the density function correctly. Now these indices is telling me 18, 17, 16, 15, etc., etc. You can't make sense of those until you do the following. So I'm gonna call this IDX, okay? And then I'm gonna print it, okay? Print IDX. What this is telling me is that the smallest value is located at point 18, at index 18, and so on. The one after it is 17, the one after it is 16, and so on. So arcsort gives you the arguments that correspond to how the array should be sorted, or how, where the smallest value is, the next small value, the next small value, and so on. Let me give you another example. I'm going to create an arbitrary array called A, np.array, and I'm going to put 1, 4, 3, and then 6. Okay? Now, to sort this array, 1 should stay the same. So index 0 will not change because that is the smallest value. Now, the next smallest value should be 3. Should be the value 3. In other words, that is, okay, let me use other numbers. Let me use 1.1, 4.2, 3.3, and 6.5, okay? So the first, if I want to sort the array, I leave 1.1 where it is, and then I got to put 3.3, and then 4.2 or 6.5 is left where it is. Arcsort gives you the index that sort the array. So if I put idx equal p.arcsort a, and then idx, it's going to give me that reading that I just showed you. 0 is the index of the first entry. It's not going to change. We're not going to change 0.1 because that's smallest. The second entry for the array should be locate index 2, which is 3.8. And then the entry after that is 4.2, which is located at index 1 in the original array. And finally, 6.5 doesn't change location. These are the indices, the order that sorts the array. And then how do I sort it? All I have to do is say A, put IDX, and see what happens. Now it sorts the array. So in other words, it takes A0, and then A2, and then A1, and then A3. Think of it this way. A0 would be the first entry, and then A1 would, A2 would be the second entry, and then so on and so forth. Okay. So now apply. Now, what's so powerful about this is then I can take these indices, apply to the independent array, and also apply them automatically to the dependent variable array. Because remember, I need to rearrange the dependent variable that it corresponds to the sorting of the independent variable. That is why this is so powerful. And it's done in just 2 lines of code. You do IDX is arcsort. We're going to sort the density array. Then we create a new array, call it row sorted. That's row IDX. We print row sorted. And then the new temperature is TIDX, which is going to rearrange T so that it corresponds to row, to the sorted row. Notice now what happens to row, it's been sorted correctly, but T has also been flipped automatically in this case, so that we maintain the pairs next to each other. If this is too much for you to understand, just keep your eyesight on these lines because you're going to need them in real life. Okay? I might give you arbitrarily arranged data pairs. You got to be able to sort it out like this to do linear interpolation. Now I can do the interp on the sorted independent variable, and what I get is 150, exactly as we expected. All right. I'm gonna leave room for some discussion. Wow, 12:05 exactly. I'm gonna stop the stream right now, and I'll leave room for some discussion. Okay.